what we did the last 2 times we were together, we talked a bit about the DLP, the discrete logarithm problem, in particular last week. And then we developed the Diffie-Hellman key exchange. What I hinted last week is that one really cool thing about the DL problem is that you can do a lot of other things with the DL problem. Okay, you can build general crypto system and you can provide different crypto applications. And we're doing one thing today. We talk about how to encrypt. Right now we have the DL problem, which was kind of a nice thing to do. But the only thing we can do thus far is do Diffie-Hellman key exchange. And now what the next 90 minutes are about is how do we encrypt data. First I want to bring the basic idea across. Then we talk about Elgamal Encryption, which is quite famous crypto system and used in practice. And then we talk about what are the computational issues involved here. Okay. So let's start with chapter number 1 of today, encryption. With the discrete log problem. Okay. First, so before we actually start doing DL and cyclic groups, blah, 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 and generators, let's take a step back and look what can we do with public key in general. And this is kind of an overview I omitted so far because I didn't have time actually the last 2 or 3 times we met. So what I'm going to show you now is come up with a little table here and give you kind of an overview what we can do with public key cryptography. I think this is quite important what you're going to see the next 3 minutes for practice. Okay, it's just factual knowledge. There isn't anything to understand, but just that you get this classification. So first, what can we do with public key algorithms? Okay. So what we can do, a really fancy term for that is to talk about a service. Sicherheitsdienst, okay. And there are 3 main things you want to do with public key cryptography. The first thing you want to do is key exchange, and we know how to do that. The second thing is digital signature. And thirdly, encryption. Okay, and here we look at the algorithm family, maybe. Let's call that fancy. Use some fancier notation here. So there are really only 2 big families of public key algorithms for practical use. The one is RSA, and what we used RSA for so far was mainly encryption. But you can also use it for key transport. I think I did that here. Okay, you just encrypt a session key and encrypt it with RSA, so you can use it for RSA. This is what we did so far. The other major family, and that's what we're doing right now, is the discrete logarithm family. I just call that DL here. Yeah, maybe DL, and then we have DL in ZP star, with this modular P arithmetic, exactly the stuff we've been doing for a few weeks by now. So key exchange, we use Diffie-Hellman for. Encryption, this is what we're going to do the next 80 minutes. This is Elgamal. Okay. And this is kind of what we did already, or going to do in the next, today. And then what we're going to add in the weeks to come is digital signature. Again, you can use RSA digital signature, which is almost identical. So we're going to do that in 4 weeks or something like that. Or 3 weeks, 4 weeks, I think. What is missing here, what we have to do here is digital signature. You can also use Elgamal digital signature. And again, this is also, we're going to introduce that in 4 weeks or so. Elgamal. And then we have the two big type of DL problems that are used in practice. One is with modular P arithmetic in ZP star. This is what we're doing right now. The other thing is, the other thing that we can use is elliptic curves, which we start next time. And with elliptic curves, you can again do everything you can do with modular P arithmetic. You can also do with elliptic curve. So for key exchange, you do ECDH, elliptic curve Diffie-Hellman you can do. For encryption, you can do, for digital signature, that's maybe better, elliptic curve DSA. And here I'm sorry here, you also have to add at this point Elgamal plus DSA, the digital signature algorithm. Okay. And encryption, there's also an elliptic curve variant of Elgamal out there. Okay. So these are all the things you can do. What we're going to do here in the lecture is, maybe check that off. So definitely going to do this here. We are definitely going to do elliptic curve Diffie-Hellman, and depending on time, we might do one of these two here. Okay. We're not doing ECDSA, it's in the book. All of that, what you see here, is in the book. So if you're really interested, you can study by yourself. So, but the big things we want to do, today we have to do Elgamal encryption. The next 2 times we meet, we're going to talk about elliptic curve Diffie-Hellman. And then once we start doing digital signature, we're doing RSA digital signature. Maybe we're going to do Elgamal digital signature. Okay? So this is kind of the universe of public key algorithms. One more factual statement. So as you see, there's 3 families. There's integer factorization, RSA-ish type of algorithms, and there are 2 types of discrete logarithms, ZP and elliptic curve. Okay. In addition, there are another 4 or so other types of public key algorithms, and there's somewhat of a renaissance, a Wiedergeburt of them. They were most of them were proposed in the 1970s, 1980s. People haven't been using them, mainly because they're pretty slow and have huge keys, like megabytes of key for one key. Right now there's somewhat of a renaissance, so people start reconsidering them. They are not used in practice. They might be used in practice in a few years, we don't know. And there's an advanced lecture, master level lecture by Professor Wolf on these. The fancy term for them is post-quantum cryptography. And at some point I'm going to tell you why they're called that way, but just to bear in mind, so you could extend that there. If you're very systematic, you could add probably 4 more algorithm families here. They're not used in practice, and for an intro course we're not going to do that. Okay. So now we want to look into encryption with discrete logarithm problem. Okay. Now the goal. develop an encryption scheme from Diffie-Hellman key exchange. So what we're doing here, we're looking at Diffie-Hellman key exchange. You know, Alice and Bob agree on a session key, and normally we said, okay, the session key can be used. You know, Alice and Bob are communicating stuff back and forth, and at the end there's KAB, right, the session key, and then we say, why do we do that? Well, we can nicely use that as an input for AES. And now what we're trying to do now is to encrypt without using AES, just using this native DL problem, so only this modular arithmetic to encrypt stuff. So how does this work? We have Alice and Bob, and we have this domain parameters alpha and p, which are just known to everybody, right? So Alice computes her parameters. She picks, and I give you now a very compressed version of Diffie-Hellman because I already showed you Diffie-Hellman twice. So it's very compressed. Lowercase a, klein a is a private key. She computes a public key. Bob does the same here. They exchange their respective keys. Bob's key, Alice's key are going across. Now both sides compute their session key. So Alice takes public key from Bob, raises it to her secret power. And she obtains the session key KAB, and Bob does the same. He takes A coming from Alice, raises it to his B power, and he computes alpha AB. Modulus P. Okay, so this is plain old Diffie-Hellman, right? Again, that should be really boring to you because it's the third time I'm showing that. You did, I think, 2 homework assignments dealing with that. So now the question is, as I said before, you can use KAB as a plug-in for triple DES or AES or whatever your favorite symmetric algorithm is. But now we don't want to use a symmetric algorithm. We just want to encrypt. Any idea what can we do from here? How can we use this KAB to encrypt a piece of data? Let's say you just want to encrypt a credit card number. What's that? XOR is a very good example, yeah? And I'm never really sure why people don't use the plain old XOR. This is essentially an addition, right? XORing. It's good, and it would probably work. But what is the next complicated thing? We can do addition and multiplication. And that's what they do. So what you take your message, your plain text, your credit card number, whatever, 200 bits or something, and you multiply that with the secret exponent, with the secret key here. Okay? This is what we're going to do here. So we have a now message X or plain text X, right? So if Alice wants to encrypt, she computes the ciphertext Y as follows. She takes X and she just multiplies with that. Okay? She's sending that over. And what does Bob have to do to get rid of this multiplication, to recover X here? What does he have to do? Yeah. Exactly. Compute the multiply with the inverse divide, right? But what we really want to do is multiply by the inverse. So Bob recovers the plain text x by taking y and multiplying with the inverse of the session key. Okay, and this is okay. So on what is I think is very important, this is essentially this fancy Elgamal encryption scheme is essentially like that. You do plain old Diffie-Hellman, you do encryption. Except if you look in our book and all other description of Elgamal, it looks much more complicated and quite different. It's not. But it's very important to me. Elgamal is almost identical to what you see here. The only thing you do two things now. You know, if you look in our book or in all other books, first of all, you change the variables. So you come up with fancy names, right? You don't call that A and B anymore. You come up with funny names, which you can do and which is only confusing for you, which is stupid. The other thing, which is not stupid, you can reorder the communications in which sequence you send which parameter over, okay? And then things become a little bit more efficient. And that's what we're going to do now. But this is the basic idea. Everybody understood what's happening here? You do a plain old Diffie-Hellman, you end up with the session key, this one party and the sender multiplies with the session key. This is kind of, you can view that as a masking operation. The receiver multiplies with the inverse. That's the basic idea. So mathematically, algorithmically, this is the same thing in Elgamal. It looks a little bit different, you know, the next 50 minutes, what I'm going to show you. But it's basically this happening. Okay, and I think it's very important to make this link. Elgamal is nothing mysterious. It's not yet a completely different crypto system. Elgamal is just one little variant of Diffie-Hellman. Okay, so this is what we're going to do now. So that's, we're already done with section number 1 of today. Okay, so now we talk about Elgamal encryption. I put here 2 remarks, okay? Because I want to have the protocol I'm going to develop. I want to have just underneath. You can put these remarks wherever you want. 2 remarks. So was Elgamal encryption was invented I don't have the exact year, but I think it was around 1985. Very similar to Diffie-Hellman, but with Reordering, Umordnung, okay, reordering of steps. And then I would say the literature is pretty much 50-50 split between calling that Elgamal, you know, writing Elgamal, and calling it Elgamal with an uppercase G, okay? And actually my old lecture notes, I always spelled it this way, but then when I wrote the book, I did some research and it seems that this is the more official spelling of the name. He's Taha Elgamal, a very famous cryptographer, it's a last name, okay? So, okay, so let's look into that, and we're going to jump back and forth between this new protocol and the old protocol. Okay. So again, we start with Alice and Bob. So one thing that is changing now, if you do public key encryption, the public key encryption, we had this analogy, before the break of mailbox. We have a mailbox. If you want to send somebody a letter, it turns out in the old days we only had symmetric key algorithm, and Alice and Bob have to know the same key. Now the model for public key encryption is Bob is going to be the receiver of the message. Okay, so if he sets up a public key encryption scheme, what he does, he's generating two keys. He's generating his own private key, which he only knows, but also his public key, and then Bob pushes this key out. Okay, so it's not so much like a jointly thing, but something that's originating from Bob, and this is what we're doing here, namely that alpha and p, which were these domain parameters, which were shared by everyone, is now originating from Bob. So Bob comes up with alpha and p. So he chooses, Bob chooses p and a primitive, which is a large prime, and a primitive element alpha. Okay. And now he has to start computing his keys. First, he computes his private key, which we call D. Does anyone know why the private key of Bob is called D and not S or V or beta? What is he going to do with the private key eventually in a public key encryption scheme? Yeah, he decrypts. You got it? Decryption? Okay. So that's why it's in RSA, it's more pronounced, right? You have the RSA exponent D for this is a decryption exponent, and E is the encryption exponent. One is a public key, one is a private key. Okay? So we're going to need that down the road at the end of the protocol here, right? In 10 minutes, we're here. At this point, we need the D for decrypting the message that's coming. So this is from this set 2, 3, up to p minus 2. It's essentially from the p, and you kick the first and the last element out, 1 and p minus 1. The public key is called beta in the literature mainly. And now already, this is a nice thing about discrete logarithm systems. There's always, you want to come up with the DL problems. The DL problem is always so we have three values here, alpha, x, and a, right? What is always the secret key here? What is the thing? What is the thing that's hard to compute? X, right? It's computing the logarithm. That's why it's called the discrete logarithm problem. So the thing that is hard to compute is always the private key. Okay. What is always a public key? Not X, right? This is a private. So what's left here? Alpha or A? What would you say? A, exactly. This is always how this DL systems work, right? What you have in the exponent tends to be the private key. The result tends to be the public knowledge, the public key, at least a non-secret value. Okay, so you compute alpha to the D, what P. Okay, so what you do at this point now, you sending over the public key, which is beta, but not beta alone. This is kind of the equivalent what you did here, right? You send B over, But you're also sending, what else do we have to send over in this setup here? What is it Alice needs to know? Yeah. P, exactly. And alpha, right? Again, that was this difference before. Before we had alpha and P as domain parameters, so everybody in the domain in this region knew that. And now because Bob generated them, he has to tell Alice what they are. So, and now if you compare that what we did above here, so if this is step 1, then this is equivalent to here, sending the public key over. So what does Alice have to do? Well, Alice also has to compute her keys, and we're going to change names here. So Alice chooses klein e, right? Again, from the set 2 up to p minus 2. And she computes, so this is her private key, right? And what you do with the private key, you always put that in the exponent of something, right? You do an exponentiation. So she computes alpha raised to the i's power modulo p, and this is called ke. And that is the ephemeral key. Does anyone know, anybody here Greek or Latin, Leistungskurs, what that means? 100 smart Abiturienten. Does anyone know what that means, ephemeral? Das heißt zeitweise oder vergänglicher, mit mehr Pathos. So it's like a temporal key, which is not for long, but only for a short period. Okay. A non-long duration key. And this is actually often used. This ephemeral key is a standard notion, standard terminology in cryptography. Okay, so and we use it for the first time here. So that is not a long-term key. And if you again compare that with what we did above, so this is computing Alice's public key, if you wish, right? So if this is step number 2, this is equivalent to this here, right? Okay. What do we do next? Well, Alice computed, I'm sorry about all the shoveling. So, Alice has her own key. She gets she's getting the key from Bob. So what Alice does, she computes a session key. And we do the same here. And now the session key is called K sub M, uppercase M. And what do we do here? Well, just as above, you take beta, which is Bob's public key, and Alice raises this to her own secret power, which is the I. Okay. Any idea what this AMP stands for? Could be master key. Actually, we're going to talk at some point. We're going to talk about master key, but it's not master key. And any other idea? This is KAB. This is equivalent to KAB here. And what are we going to do with KAB? I mentioned that before once. We multiply, right? And another word of calling that multiplication is we use it as a masking. Okay, so KM is a masking key. Okay. Oh, and by the way, these names are not necessarily you called that way in Elgamal. It's just the way we do that here. In our book, I think it's very useful. So we have the masking keys, and which color do we have used? Let's use yellow. So this KM is equivalent to computing is equivalent to the session key, what we call KAB here. Okay. You need 6 different colors today. Okay. You can do that in blue, everything, that's fine. It's just, I like colors. So once Alice has the session key KAB, once we're here in the protocol, she can also do the actual encryption, right? Nothing prevents her. So before we do anything else, she does the next step of the protocol. Alice computes the ciphertext Y, which is X times KAB, except it's not called KAB here, it's called the masking key. So she masks this, color number 4. She masks the plain text X with the masking key, with the okay. So if we follow the protocol, if you stay really close to this Diffie-Hellman variant, what you would do at this point, you send Y over. Okay? And is this everything she has to send over, or what is missing? What is the other thing that hasn't happened here? Yeah. Exactly. What we haven't done here to send, Alice's public key over, right? So, this is what we're going to do here. So what is the public key? It's not I, right? It's the secret exponent, but number 2. This ephemeral key, this temporärer Schlüssel, this KI, is also sent over. So if we give this, and this is one of the main difference between Diffie-Hellman-based encryption in Elgamal is this reordering of the communication. So if we call this step number 5, sending over of the information, this is really this, but also this here. We merge those 2 communications together. You can stay with one color, okay? It's just, I want to have nice, colorful blackboard here, okay? So you can stay with one color. And now at the end, Bob has to reassemble everything. He has to do whatever he did before. Oh yeah, that's a good question for you. What does he have to do first here? What is left for Bob to do? And you can just look, what are the things that we don't have, funny circles? What does he have to do? Well, he eventually wants to do this here, right? He wants to compute an inverse and do this unmasking, right? So, but before he can do that, he needs KAB. And what was KAB? This is the masking key here, right? So he has to compute the masking key. And what does he have to do to compute KM here? Does anyone know? Yeah. Exactly. He has to take KE, which is a public key, and compute also KM. So he has to do this part first, right? He has to compute the Diffie-Hellman key, if you wish, the session key. How does this work? For computing the masking key, KM. He takes the ephemeral key, this temporary key, raised to his secret power. What is his secret power? His private key D. And it ends up being KM again. Six. What am I doing here? Okay. Once he has the session key, he again does this very last step. X is y times the inverse. What do you look P? Okay. Which color is it's orange? Yeah, okay. It's a little bit goofy because they look the same already. So this is 7 and this is 7. Okay. So okay, so I hope there aren't too many colors here. I hope you could follow. I did that pretty slow, and I did use the color to really get that across. They're essentially the same protocols. You introduce different names, which are confusing, right? You call ephemeral key and masking key, and you reorder the communication, but step by step you do the same thing in both protocols. Okay, very important. Most books don't tell you that, right? They do Diffie-Hellman and say, oh, here's now the completely new protocol and it does encryption and it's something completely new. It's not. This is almost Diffie-Hellman. Okay. So now I want to do the next thing, namely actually prove, which we rarely do, proof of correctness, show that really you get the right result out, it works. Proof of correctness, that means Alice, what maybe is done here, what Bob decrypts here in the step number 7 is actually the plain text. So he actually recovers, the plain text that Alice encrypted. Okay. That means Bob computes and we just look at this very last equation here. Y times the inverse of the masking key. And now we look step by step what's happening. What is the masking key? The masking key was computed here as ke raised to the dth power. So we simply substitute. We have to take the inverse. Okay. So next thing, we look what is y. Where is y coming from? Well, here's y. Came over the channel, over the internet, and it was computed as this way, right? Y is x times the masking key. So y is being replaced by x times the masking key times And we're getting rid of the parenthesis of the Klammern here, right? So this is k to the minus d. Okay, next step, we're going to drill deeper in these keys. What are the masking key? What is the masking key? The masking key is beta to the I. Beta to the i's power. And what is KE, the ephemeral key? Where was that computed? It was computed at this point here. KE is alpha to the I. So I'm just doing very stupid substitutions at this point, okay? So we're almost there. And right now, it doesn't look, there are a lot of different variables. It doesn't really look as though things would resolve nicely. What is our goal here? What do you want to show? We want to show that y times the inverse of the masking key is equal to what? What do we have to show? We want to show eventually this is equal to x, right? So just to give you a little bit idea what the strategy behind what we're doing here. So what we would like to have that y times km minus 1 is equal to x. You have all kind of really annoying other junk here, right? So what do we have to show? What does this have to become equal to here? 1, right? X times 1 is x. So and that's where we're heading to in this direction. So now what is left is beta. We can do one more substitution where it's beta. Here. Beta is alpha to the d. Okay. You get the idea now? And this is similar to Diffie-Hellman, right? With Diffie-Hellman, you had alpha to the AB on the one side. On the other hand, you had alpha to the BA. And it turned out to be the same thing. And this is happening here as well. Okay, and all of that is modulo P. So I should have really used the equivalent symbols here. Okay. Done. Okay. A lot of substitutions. All these steps, this is essentially showing that Diffie-Hellman works. It's the same proof of correctness that we did with Diffie-Hellman. So now let's talk a little bit more about this protocol. And so far maybe I made it sound too simple. I said this is Diffie-Hellman, and this is just this Diffie-Hellman again, and you use it for encryption. And there's actually quite a bit of things we can discuss from here out. So let's have a whole set of remarks, okay? First remarks is the advantage of Elgamal over direct Diffie-Hellman encryption. And what I mean with Diffie-Hellman encryption is this here, right? This protocol, which actually most books don't even do that and don't talk about that, right? This is just what we do here in this lecture. Colon, Doppelpunkt. Let's say if you only encrypt once, computation is completely equivalent. You have, you do the same number of steps, the same number of exponentiations, and so forth. The thing is, once you start encrypting your second plain text, so if Bob receives more than one message, but he gets another message or a message from another person or something. If we stay with this here, or let's say if Bob does this with Alice, and then Bob wants to do that with Christine, for instance, right? In this setup, we again have to do all the steps all over again. What we do here is, it's not quite true. Bob sticks with his public key, so his public key is fixed. I think this is one of the differences here. Advantage of Elgamal over direct Diffie-Hellman encryption. His public key better is fixed. And alpha, p are chosen by him. I don't know whether that's really an advantage. Maybe that's a difference, would be a better word. Okay. So that's the first remark. Now we're getting a little bit more interesting. It also has to do with security. So this beta is fixed. Okay. Every time somebody wants to communicate to Bob, send him an email or whatever, that beta stays the same, Bob's public key. What is the other public key? The other public key is this KE here, right? This is number 5. This is the other public key. And now it's very important. This public key has to change every time you send him a message. Don't leave that the same. There will be a homework problem on that, right? Or I'm probably going to talk about that today too. So KE must be different for every plain text. And we're going to show later, we have time, I think today, I'm going to show you why this can't change the same. So that means this one public key beta can stay the same. The other public key, this ephemeral key, has to change. And this is why we call it ephemeral, temporärer Key. That's nur ein zeitweiser Schlüssel. If you change the plain text, you want to encrypt your second plain text, choose a different key. You can't encrypt them under the same key. And now it probably comes the most interesting comment. Okay. Which is related to this comment. Let's say you take the same message, your credit card number. Okay. Your credit number is X. You encrypt that, you send it to Bob. Bob is whatever, Amazon.com or eBay or Facebook with a secure session. Credit card number, okay, do that the first time. Now next day or an hour later, you're going to do another purchase, you buy another really exciting cryptography book, right, at Amazon.de. Use your credit card number again, okay? What will happen to Y? Will Y be the same or not? That's my question. So you encrypt the same X twice. So X stays the same. Okay, let's. So this here is this is our encryption function. This is Elgamal. You send X1. And then you sing X2, but they happen to be the same values here. Okay. Obviously, you get Y1 out. You get Y2 out. The question is, these are the same values. You encrypt the same plain text twice, right? Your same credit card number, same whatever, 32 bits or so. What's going to happen with Y2? Is this true? Is y2 equal to y1? This is what happens with AES, right? You encrypt with the block cipher twice. Is this true or not? No. Yeah.
No, it isn't. We choose a different KE, so we choose a different I every time, and this changes the
Genau. I just told you, don't reuse KE, right? We have to chase KE, and how do we change that? Well, this I here, dieser geheime Exponent, this has to be different. Every time you encrypt, I changes, that means I changes here and KM changes. So that means every time you use a different masking key, right? This is what we call masking, the Maskierungsschlüssel, this changes. But this is wrong. Okay? So even if you encrypt the same two values twice, you get a different output, which is cryptographically very, very nice. So, and now, this is now a change from our normal encryption model. You know, we saw this very, very often when we talked about symmetric algorithm, right, first semester. So what we normally had, we had the key going in, or KAB or so. But what we do now here, we have K public going in, which is, the public key is beta, right? This is kind of the main, if you wish, the main key that we use for encryption, but this is not the only key, because what we also use, we use a randomization parameter, namely I here. E in German, right? So, and this serves as a randomizer. Okay, this randomizes the encryption here, and a fancy term for that is now Elgamal is a, in quotation marks, because it's a new term, probabilistic encryption scheme. Und in Klammern, in parentheses, unlike schoolbook RSA. Okay. Was? Nee, es ist misspelled hier. Probabilistic. Thank you very much. Probabilistic. Okay. Zufall, ne? Zufälliges. Okay. This is a very nice property of cryptosystem. Actually, more modern, more theoretical cryptography wants to have exactly this property. If you encrypt the same thing twice, you want to have a different ciphertext. Oh, we did talk about that. We did talk about that in the context of modes of operation. Does anyone know if you do like one of the chaining modes or so, we also have one parameter to make AES encryption probabilistic. Does anyone know what that is? This is IV. Do you remember the initial vector? That has a similar role. For every encryption, you should switch your IV if you go back in the lecture notes. Okay. What is next? So, okay, we're done with chapter 2. Okay, so now let's turn to the computational aspects. And by the way, this was the most important part of today, so you can go back to sleep from now on. Okay, the rest is pretty minor what we're doing here. I'm exaggerating a little bit, but this is kind of the main thing I wanted to teach you today. So the rest is cure, if you wish. Okay. So that's chapter number 3 of today. So let's look what we have to compute here. Alice and Bob have to compute. So what do they have to compute? They have to compute the this here beta, which is alpha to the d. They compute the. Then they have to compute the ephemeral key and the master key. Ke is alpha to the I, and the master key, which is beta to the I. How do we do that? How do we do this exponentiation? My question is, which algorithm are we using? That's it. This is square and multiply algorithm. Very boring. We did that 6 weeks ago or so. Okay, in context of RSA. This is easy. So now we did all computations. We showed how we compute this here. We showed how we computed this here. We showed how we compute this here. Which step is left? Well, this multiplication, we're not going to talk about that. So this is a modular multiplication. That's trivial. What is left are these two steps here. Okay, and this is where it's getting a little bit interesting. Here we can apply a little trick. Okay, so the question is, how do we compute Km, which is Ke mod d, and then or maybe let's break that down. We compute Km, and then we need the inverse, right? And then thirdly, we compute okay. In naive assumption would be the following. What do we have to do? What kind of algorithm do we use at this point here? Yeah. Not here, but you mean here, right? Yeah, exactly. So here we use the extended Euclidean algorithm, very good, right, for computing the inverse. And what do we have to do here to compute Km? Square and multiply again, right? So it looks, let's first do square and multiply, and then let's do Euclid, right? It turns out you can merge those two and do a single square and multiply. And how is that? This is pretty easy. I'm going to show you now. Okay, and this is, we don't have to do square and multiply. We don't have to do Euclid. So we had many weeks ago, we had Fermat's little theorem, Kleine Fermat, which stated with these parameters that we have here for all ephemeral keys, so for all elements Ke in ZP star, it holds that does anyone know what Kleine Fermat is? Does anyone have recollection? Any idea? I never ask you to memorize that, but it would be very encouraging if there's some very smart students with very good memory that would remember. Anybody makes me happy today? No? No? Okay, so you don't have to make me happy. So you do this here, so you raise it to the p minus 1 power. but does this anybody know, please? What? Eins, genau, eins. Yeah, it's 1. Okay, very good. Modulo P. That was kleiner Fermat, one of the properties which we didn't prove, but in colleagues in discrete mathematics will prove that for us, for me. So with this knowledge, we get a very nice solution to this problem here. So what we really want to have is the inverse of the masking key, right? So, but how was the masking key computed? Well, the masking key is computed in the previous step by an exponentiation. Okay. And again, everything is mod P here. So this is still not too exciting, but now comes the trick. But we can, let's do that here. I multiply that by 1, right? I can multiply things by 1. Anybody has an idea what I have to do now? What do I substitute the 1 by? Well, by this expression here, right? P minus 1. And we're almost there now already. So you simply add up all the exponents here. Okay, so that means so the last step here, really step 6 and 7, but let's just leave it by step. Step 7 in Elgamal becomes x is what we can do here, this is simply y times p minus 1 times d modulo p. Okay. Okay. And that's all what I wanted to tell you here, but since we have time left, which is rare, let's talk about attacks. And it's not long. We're done in 10 minutes, okay? Maximum 10 minutes, okay? So finally, we want to talk a little bit about attacks here. So it's chapter number 4. So the first attack that we can run here, if we're a bad guy, attack means, oops, wrong board. Attack means he's a bad guy, Oscar here. He's bad, right? So he can observe the channel. He's a passive attacker. He can observe the channel. He would like to compute X here. Okay, let's see how we can do that. Again, it's similar to the discussion we had with Diffie-Hellman and Diffie-Hellman problem and so forth. He has most parameters. This is all the public parameters. What are the 2 parameters he does not know? What are the 2 secrets that he doesn't know? What? I'm listening, yeah? He doesn't know here, this. Exactly. This and D, very good. And this is similar to Diffie-Hellman. These are the two secret exponents. Once he has I and D, he can decrypt the message eventually. So the first attack is compute the discrete logarithm problem. That means either he tries to compute lowercase d, which is the logarithm of beta to the base alpha, logarithm of beta to the base alpha. And once he's done that, maybe to sketch that, what can he do if he knows d? Well, he can do the same thing that Bob does here, right? Once he gets this from wiretapping, from Lauschen in den Kanal, he can do this experimentation and he can decrypt it. So once he has that, he can compute the masking key, and then he can compute right? In this case, he is like Bob, right? He has Bob's private key. Or the other thing he can do alternatively, he can compute the other secret component I, and let's just see what happens if Oscar were capable of doing that. What is I? I is the discrete logarithm, again to the base alpha of ke, of the ephemeral key. Once he does that, again he won essentially. He can compute the masking key, which is beta hoch I, beta to the I, and then he computes again the plain text. Okay? What is the problem here? Well, the problem is he has to compute a discrete logarithm problem. Okay? So as the good guys, as Alice and Bob, as the designers of the crypto system, we must make sure that the discrete logarithm problem is very hard. Okay? So the discrete logarithm problem needs to be a computational How do we do that? How do we make sure we can't compute that with a pocket calculator? What is the main thing we have to do here? Long, right? Really long prime, right? 1024 bits, okay? P must be large. At least 1024 bit. And we talked about that last week. There's a whole bunch of other requirements on P and alpha, actually, which we don't treat here. Okay, so you have to watch out for small subgroups and certain other things. But the main thing for a second semester course is P must be large. Bear that in mind. Okay, you can't choose 100-bit P. I think I did talk about that. There was a DEC product in the early 1980s, so about 30 years ago almost, where they chose a 128-bit prime and that got broken. Okay, that was too easy to break even back then. Okay, so this one thing, one possible attack. So make sure that the DLP is hard. The second attack, which is a little bit more interesting, is if you're not careful, and these are the things that happen actually much more often in practice. You do an implementation of that, and somehow, Alice needs a fresh eye here. So, and where is that coming from? Hopefully from some strong random number generators, and for whatever reason, the random number generator fails. These things happen. But if it's a true random number generator, that's often extracted from some physical phenomena, ein physikalisches Phänomen on the circuit level, in einem Schaltkreis. And for some reason, this integrated circuit fails, right? And you get always the same I out. And maybe I looks really wild, really nice, randomly looking 1024-bit numbers. It's always the same comes out. And, if your piece of software does the rest, and you don't check for that, you might encrypt always with the same I. And here are the bad things that can happen. Okay? So second attack is reuse of secret exponent. Okay? So where does this come into play? Here, KE is alpha to the I, and also the masking key is beta to the I. Okay? So now, and reuse means wiederholtes Benutzen. So we have to talk about two communications, right? This is you do something again, so we need at least two communications. Let's say the first time, plaintext number 1 is being encrypted with the masking key. And sent over the channel as Y1, KE. In the next session, the second plaintext is computed. This goes over the channel. Okay, so that's the setup. And now Oscar Oscar observes this here. So Oscar observes this communication. So my first question is, does Oscar know that there's something broken, that the same I is being used? Does he know that? Yes, no? Okay, let's have a vote. Who thinks that Oscar will recognize that the I is the same? Yeah, good. And why? How does he see that? Yeah. KE is the same, right? If I changes, you would see a different ephemeral key, right? Dieser vergängliche Schlüssel, suddenly it's not very vergänglich anymore, right? It's the same KE here, right? Okay. So that's already good. So Oscar said, oh, there's something broken. It's in particular interesting if Oscar somehow manipulates whatever the smart card so that it breaks because he did something funny to it. Maybe he has access to the device and overheats the device, things like that. Okay. So what we now assume, assumption, Oscar knows X1. He knows the same first plaintext. So it's a known plaintext attack. Okay. He doesn't know the second one. What he can derive from these two equations is obviously Km is Y1 times inverse of xi. So I'm just looking at this equation and I'm reorder that. But this is also equal to y2 x2 minus 1 And that's the problem. You have this equation, and before that's the problem here. So Oscar sees KE is the same, so what he concludes is that the secret exponent is the same. But what follows from now, and this is a real problem, the masking key is also identical, right? If I is identical, both masking keys are the same. So what Oscar can now write down is say, well, this masking key is equal to this masking key, so let's put that in an equation. So he writes Km is y1 times divided by x1, but it's also y2 divided by x2. Normally he would, and now what are the unknowns here? Well, he obviously knows the two ciphertexts, right? They're on the channel, but he also, by assumption, he also knows x1. So the only thing that is left is x2. It's just a linear equation here. So he just solves for x2. x2 becomes y2 times inverse of y1 times x1 modulo p, and he computes the ciphertext as a plain text. And of course, this doesn't only work for x2, it will also work for x3, x4, x5, and so forth. So everything that Alice encrypts from now on with her faulty, her fehlerhaften random number generator, if y stays the same, or if there's a software bug, for instance, right? If the software always returns the same I here, as soon as Oscar knows one single plain text, he can compute everything else here. This is pretty bad. We are done. Don't jump up. First of all, I need these questionnaire specs, the Fragebogen. Very good news for you. There's no lecture next week. Okay? That's it. Thank you.